Right, so let's do a quick recap because we'll continue from the SMAC scheme. So we discretized the semi-explicit method equation that we had. It was, if we started with the predictor, so it's a two-step approach, right? So it's a predictor corrector approach. We predict the velocities called U stars, and then we correct them using an equation for pressure correction, which is linked to the velocity corrections. So what we discussed in the last two lectures was discretization of the predictor step for particularly the U equation. But V equation is very similar, so we don't need to write the complete procedure for that. So I'm sure you can do it yourself if needed. So we talked about, we wrote the U equation, then we followed the standard finite volume approach to integrate the equation over a control volume, in this case delta omega, and then we handled the transient convective pressure and diffusion terms separately to get expressions for the different terms, and then we summarized the equation, the finite volume formulation as this, where you had the convection and diffusion flux terms, and then the next step was to discretize them. So we discretized the convective terms using the coefficients were discretized using the center average method, and the actual unknown that we are solving for in the equation, well, in this case it's an explicit approach, but still, I mean, U is the variable that is being solved. So U is upwinded from the ideas that we are bringing from the 1D wave equation, hyperbolic equations. So this is the approach we followed, and then for the diffusion terms we followed standard center differencing to discretize the gradients or the derivative or the partial derivatives at the phase boundaries. So that's typically a finite volume approach. You discretize things on the volume. You integrate the equation over a control volume. Then you then you use Gauss divergence or Gauss's theorem to convert those volume integrals to surface integrals. So you have integrals over the surface. So you need quantities over the surface, not inside the volume anymore. It's a very interesting, a very, very useful theorem. And since we need things in the surface, we have to use some sort of interpolation or averaging to find that, because the variables are available only on the nodal points. So we use either upwinding, center average, or some other kinds of averages are available. When you study finite volume in greater detail, there's plenty of things. In fact, the key idea of finite volume when you propose new schemes is to figure out how to give an approximation for the quantities over the faces using the nodal points. So you get lots of schemes with lots of different names in finite volume. But the aim of this course is not to discuss all of those, but to discuss a general methodology of finite volume methods. And you will see when you go into applied research in this field, you'll see that you'll not use these structured grids anymore. Structured grids are where you have we have these nice squares or rectangles available where we have a delta x and delta y. Well, in a course like this, it's convenient to use structured grids. Structure means that you have some sort of structure. So if I give you some size of delta x and delta y, and some way how the delta x changes with x and delta y changes with y, you can generate a whole grid. I don't need to store the coordinates of each and every point in a file. There is a structure associated with the mesh or a grid. Okay, but unstructured grids, on the other hand, are grids. You may have seen those pictures of triangles and random elongated triangles and so on. So basically, you just put some sort of nodal points and then you connect them through lines to make triangles. In a 2D mesh, in 3D it becomes tetrahedrons. There are other kinds of meshes available as well. Unstructured means there is no structure as such. So you have to store the coordinate of each and every point, nodal point, and you have to store the information of connectivity between different points. So that means it's an unstructured mesh. So storing the information becomes a tedious task, and how to, when we write loops to loop over all the points, we have to keep revisiting that file where the information on nodal points and connectivity is stored. So that brings in some sort of data structure kind of a picture into the algorithm, where you need an understanding of data structures, to how to store data in an effective way. So you'll see that happening if you work with development of CFD codes, because most of the codes use unstructured grids because of the convenience of handling arbitrary shade boundaries. Because if your boundary is an arbitrary shade, which it is in most cases, like an aerofoil, for example, of an aeroplane, then it's difficult to make rectangles and store because it's a curved boundary. Okay, so you have unstructured grid so that it can take the shape of the boundary nicely by putting points along the boundary points. Anyways, we won't say much more about that. That's for an advanced CFD course where you learn how to deal with that. But for this, I think that this idea is enough. So this was predictor step. Now let's talk about corrector step as well, so that we are able to complete the algorithm. So for the corrector step, if you will recall, we had a pressure Poisson equation. P prime here is the pressure correction. So we are solving for the pressure correction. Remember that. Once we solve for pressure correction, then we can find the pressure at the next time Pn plus 1 as Pn plus P prime. And this U star is already known from the predictor step, the step number 1. So U star vector is in our 2D discussion, it's the components U star comma V star. So once you solve this equation, then you can find Pn plus 1 as the pressure at the nth time plus P prime that you've just solved. So let's discretize this using the finite volume method. So this time we'll go very quick because we have already learned how to deal with this kind of an equation in the stream function equation. If there's any question, then you can always ask. Otherwise, I'll keep moving on. So we use the Gauss divergence theorem. So we get a surface integral. On the right side also we get a surface integral because we have a divergence of U star. So we get a U star dotted with the infinitesimal area vector. So we'll call this A. So let's make so this is our control volume under consideration. So we have point P at the center. Then capital letters are used for nodal points, and then small letters are used for boundary points, boundaries here, faces. And so let's work with the left hand side first of A. So this becomes a summation over the 4 faces. It's a surface integral. So we have 4 faces: east, west, north, and south. And then we get grad P prime over the face dotted with the area of that face which is gamma f. So delta gamma f, because d gamma is used for the infinitesimal, and this time we have 4 areas which are delta gamma: east, west, north, and south. Right. So this time we'll discretize as well. So first let's simplify this. So on the eastern face, we get grad p prime dot. So the area vector is along the I hat direction on the eastern face. So if you do I hat dotted with grad p prime, you get del p by del x, del p prime by del x, times the area is delta y. Similarly, we'll have expressions for the other 4 faces. On the western face, the area vector is in the outward area is in the minus I hat direction, so we get a negative sign. So this time we will discretize this as well. So del p prime by del x on the eastern face can be written as p prime on the eastern node, capital E, minus p prime at the control volume node, that's capital P, divided by delta x times delta y. So this is how we are discretizing del p prime by del x on the eastern face. And I won't repeat that. I mean, you can proceed similarly for the all other 3 terms. We have done this in the stream function equation, so I don't want to spend too much time on writing things in detail here. If you have confusion, you can always go back to the stream function discussion we had. Right, so let's now go to the right hand side of A. Which was rho upon delta t times u star dot d gamma. So you'll have, so let's expand this. So on the eastern face, we will get only the I component, so that's u star scalar, and the area is delta y. Now on the western face, it's going to be a negative sign for the same reasons discussed earlier. Now what about northern face? So if you expand this u star vector, you get a u star I hat plus v star j hat. Now that this vector dotted with a j hat gives you only v star. So we get a v star times delta x. Sorry, this is on the east, west, north, and then we have v star over the south face times delta x. Alright. So now u star on the eastern face has to be somehow written in terms of the nodal points. So we can do a center averaging here. So I can write u star over the eastern face. So I'll again do it only for the eastern face, and then using same idea as you can do it for the other faces. So this becomes u star on the eastern capital E node minus, plus u star over the node CV node P divided by 2. Now you always do it u star E plus u star P divided by 2, and that is because our grid is uniform. If your grid is non-uniform, then you'll have to figure out where the face lies in terms of how far. If it's closer to the eastern node, then you have to do the interpolation accordingly. So we are doing some sort of a linear interpolation between the 2 points. Okay. Any questions? Right, so when you you can now simplify this. I'll not do it here, and then you can use your indexing, I comma j indexing that you're using, so that you have things written in terms of indexing, and then you'll have to write a loop to visit all the interior points. So ultimately you'll get an equation which will look very much like the stream function equation, or in fact here it comes out to be similar to the finite difference discretization that we had seen earlier. Again, that we saw in stream function approach. Okay, so you get an equation in p prime terms, which is sort of implicit in the sense that there's no explicit nature here. They're all there's no time as such here. So it's you have to solve for all the p primes together. We'll have p primes for north, south, east, west, as well as the node capital P here. So you have to solve that equation. So we can use a Gauss-Seidel method to solve it with the ideas of over-relaxation, successive over-relaxation, and so on. So those ideas, you know how to solve these linear equations iteratively. Or what you can do is you can also use pseudo time stepping. So you can add a del p prime by del t term, and then you can use an explicit approach to solve it by time stepping till steady state, whichever approach you would prefer. Right, so this is solving for p prime, but that does not give us un plus 1. The aim is to get un plus 1. So once you get this, then you have to correct the velocities using the velocity correction formula. Which is this one for un plus 1 and for vn plus 1 as well. Remember, u star and v star are already known. They were solved in the predictor step. That was step number 1. So now that you know p prime, you can get del p prime by del x at all interior nodes, as well as del p prime by del y at all interior nodes, to get un plus 1 and vn plus 1 at all interior nodes. So job done. So one step is completed. Any questions? So if you look at the pressure correction equation again, we had this divergence of gradient of p prime equals rho upon delta t times something. Sometimes what we do is we absorb this delta t by rho into p prime, because p prime is an unknown, right? We're solving for it. So let's say our unknown is not just p prime, it's p prime times delta t by rho. That gets rid of this delta t, rho upon delta t that we have to write everywhere. So when you solve it in the end, let's call it p double prime. So that p double prime that you solve for is not p prime, it's p prime times delta t by rho. If you want to extract p prime from there, then you have to divide that by rho upon delta t. Okay, so we can define. So I'll just write it down because that is typically what is done. So if you look at some commercial code, they'll be solving for p prime times delta t by rho. So that confusion has to go away. So you solve for p double prime, and when solving for un plus 1, you need p prime times delta t by rho anyways. So even this velocity correction formula also gets simplified. Sometimes the negative sign also gets absorbed into this p double prime. So that depends on the situation. But ultimately you're solving for a variable which includes p prime times some constant. So you should know what that constant is. Otherwise, we may not be able to write the velocity correction formula properly. Right. Now we haven't talked about boundary conditions till now. We talked about the interior point, but what about boundary conditions? Boundary conditions for actual velocities is much easier because we know what the velocities are. For example, in the backward facing step that we had, so let's say we are solving the backward facing step problem that we have solved using the stream function vorticity approach in the past. How do we specify boundary conditions for the predictor equation, which are kind of simpler? But what about these pressure correction P prime? What sort of boundary conditions are used for pressure correction? So let's discuss that. So actually, what is known? Actually, we know that on the walls we have a no slip condition, and it's a not a permeable wall, so that means that no flow can pass through the wall. So if it's a non-permeable wall, then V is equal to 0, and if it's a no slip condition, then U is also equal to 0. So we get this same no slip on all the walls. At the inlet, we know the velocity profile, so it's a known velocity profile. So let's say it was, I think we used a parabolic profile. Some U naught and V is equal to 0. U is equal to U in. U naught was used for something else. And at the outlet, we know that this is not very straightforward. No boundary condition is given from physics. We have to figure it out from the situation. So if it's a very long backward facing step, like a very long pipe, it's a fully developed flow, so things will not change with X. So we can use that. So for the predictor equations, it's straightforward. I mean, you know the velocity, right? So you're not even solving for, you're not predicting the velocities on the boundaries. So there's no confusion for U stars and V stars. We're not solving for them. They are the same as what the actual boundary conditions are. So the correction is 0 for them, right? Do you agree? For the inlet, if I write UN plus 1 for the inlet, so U star, so we know that we know the U value at the inlet. Okay, so that means that there's no correction to be. So correction is 0 because our prediction, let's say we have predicted the velocity to be the same as what the boundary velocities are, and they're always the same. So there's no confusion. U primes are always 0 on the boundaries. So can we extract? So this is 0. So if U prime is 0 on the inlet, can we use that to get the boundary condition for pressure? So what is U prime in terms of P prime? Right? So if this is 0, then that means that del P prime by del X is 0. So that gives us the inlet boundary condition for the pressure correction P prime. It's a very interesting idea. And what kind of a mathematical boundary condition is del P prime by del X equal to 0? It's a Neumann boundary condition. In fact, it's a homogeneous Neumann because it's equal to 0. If the gradient was equal to some non-zero quantity, it would have been a standard Neumann condition. But if you make it equal to 0, it becomes a homogeneous Neumann. The same kind of conditions you get in heat conduction, you get it for symmetry or adiabatic situation when there's no heat flow out. So we know how to deal with these equations and these conditions for Poisson equations. So we're getting a link here that if the velocity, if the boundary condition for velocity is Dirichlet, then the boundary condition for pressure, I keep saying pressure, it's actually pressure correction. But you will see in the literature, in the books also, that they talk about pressure, but that is pressure correction. So the boundary condition for pressure correction is Neumann. So you're getting, and you will see this again and again. Okay, so just, and this is a very interesting idea. So just try to pick it up. What about, let's pick this wall, the top wall. What about the pressure correction on the top wall? So let's look at the V prime here. So V prime is 0. So no normal wall. I'm not even using a snow slip condition. So V prime is 0. So what's the velocity correction? Right? So again we get a homogeneous Neumann condition. Now what about outlet? On the outlet, we are saying that the primitive variables u and v are fully developed. Okay, so it's a fully developed velocity. So this implies that del u by del x is equal to 0 and del v by del x equal to 0. That's what fully developed means. Things are not changing with the x direction. But can I say del p by del x, del p prime by del x is also 0? Because if that was the case, then that means that our u primes are zeros. But that is not the case, right? So it's not a Dirichlet. So Dirichlet boundary condition for velocities will imply that you have a homogeneous Neumann boundary condition for pressure. So we cannot apply a fully developed condition for p prime because that will imply that your u prime is 0. But that is not the case. Okay? So we cannot use okay, so that let me say this will be wrong. So at the outlet, what we do is we specify an infinity pressure. So we say that, think of it, I mean, if you have an outlet of a pipe, then the outlet you have atmospheric pressure. Okay, so we call it P infinity. So at the outlet, typically we'll say will be some P infinity, some datum pressure, or could be atmospheric pressure. You know that in incompressible flows, we have to specify some reference for pressure. And then everything is in terms of pressure differences. Like you see the Navier-Stokes equation, it does not have an absolute pressure in it. It has del P by del X or del P by del Y. It's the difference in pressure that drives the flow. So if you think of a pipe. Now, most of your mechanical engineers if you see a pipe, if you have let's say very high pressure and the same pressure at inlet and outlet, will there be any flow? No, because there is no pressure difference. If pressure difference is the only reason if there's a gradient, and then it could be the other reason. But if pressure gradient is the only reason to drive the flow, there will be no flow. So flow happens because of differences in pressure. So the absolute value of pressure does not matter. It's the difference between 2 points. So if I specify the value at one point to be something, then the values at other points can be calculated in reference to that point. Okay. So at the outlet, we typically will use the boundary condition that P outlet is some reference pressure. We call it P infinity.
Sir, this will imply that if P outlet is a constant, then its gradient will be 0.
Between what? If P outlet is constant, P outlet is some reference pressure, then the pressure inside will be different from the outlet pressure in most cases, if the pressure gradient is there in the flow. So that is what we are calculating, right? We are calculating the differences in pressure. Okay.
It's outside the.
Yeah, outside. At the outlet, if you connect, let's say the pipe is open to the atmosphere and there is some flow happening. So on the inlet, you may have connected some sort of a pump. So that pump is giving high pressure at the inlet, and the outlet is atmospheric. So that will drive the flow. So if you know the pressure at the outlet, what is P prime? It's 0. Right. So P prime on the outlet becomes 0 because that's a correction. See, you know the pressure at the outlet. So Pn plus 1, whatever is all known. So that means P prime is 0 on the outlet. So that gives us a Dirichlet boundary condition for pressure. Now that's interesting. For the velocities, what did we have on the boundaries? On the outlet boundary, we had Neumann. So Neumann for velocity, Dirichlet for pressure. Dirichlet for velocity, Neumann for pressure. So you get the idea. I think that's it. So I just need to give you an algorithm, but that is simply a summary of what we have written till now. So that can be given in the next class, and that will end our discussion on the semi-explicit method for solving fluid flow equations using primitive variables, that is U, V and P. So in the next lecture, we will start with a discussion on semi-implicit methods, and that's a very common scheme called simple. That was given by Patankar, and that book by Patankar is already a part of your syllabus as a reference book. I have not been uploading reading assignments, but recently what we have discussed on finite volume methods is all from Patankar. So you can read that book. It will give you a good summary. It's a bit difficult to read for some, but that's okay. It's not required for you to read that right now. You can read it later, but it will help you a lot in understanding, especially because that person has given a scheme called simple, and you will see in fact, you may remember that in answers also when we clicked the schemes, simple was there, and some simpler, which is a modified form of simple. So the contribution by Patankar is huge in CFD, so you must read that, and that's a very well written book. It's a very compact and nicely written book without the use of too many equations. He talks about the ideas, not the equations. Right. So thank you. I'll see you in the next lecture tomorrow.